Thanks a lot for the introduction. Is that okay if I'm here? Okay, perfect. So yeah, I'm gonna introduce myself again for those that weren't here yesterday. So my name is Gomaa, and I'm a PhD candidate at German Research Center for Artificial Intelligence, or DFKI, and Saarland Informatic Campus at Saarland University. And as Kit mentioned, I'm gonna talk to you today about adaptive user-centered neuro-symbolic learning for multimodal interaction with autonomous system. So the title is super big, but we're gonna hopefully dissect into it together, and it's quite related to what we have seen today in the keynote. So the idea and the motivation of this work that we have already seen today, also in related work, and we have heard in the keynote that when people interact with any interface, they interact quite differently, and their behavior will be a bit want of customization, and will require some kind of personalization for them as well. And what we have as a whole schematic for this story of interaction with any interface is that most of the existing machine learning-based approach or data-driven approach, as far as we know, they rely on what is called sub-symbolic learning, or this have large amount of data that you learn on, and you create your own weights that can deal with the model. However, some other ways of doing things is a rule-based approach, where you create your own set of rules, and then we call that as a way of knowledge representation or symbolic learning. But what we have an idea is that we should have the best of the two worlds. So we would like to combine the sub-symbolic learning with the symbolic learning through a mix of rule-based approach and a data-driven approach. So instead of relying purely on one of them. So the whole idea is any agent or any, let's say, interface that have a learning agent inside it is relying on explicit and implicit sensors, or explicit way of interacting with the environment. And the implicit sensors is what we call observation, or yeah, maybe I could also use a laser for people online. So what we call it as an implicit is a set of observation or sensors that we have in the model learn from, like, let's say, gaze or speech or gesture interaction, or any kind of this signals that the user can deal in, that the system can deal in automatically without intervention of the user. However, there are other ways of getting feedback from the users through explicit feedback by controllers, or by inserting certain rules from the users online or offline. This is also some things that we're going to discuss later. And these are the way of getting some feedback from the user itself while training. What we propose is that we could use this both kinds of input to adapt our model to the specific situation, or the specific user, or the specific tasks that the user is handling, through the known techniques or known algorithms that are the state of the art in both worlds. And to do so, we can create a truly autonomous system. We are not delving into the part of having the user, as we also heard in the keynote this morning. We are not in the part with the manual. We are talking about a fully autonomous or zero control kind of agent, or zero control kind of interface. However, we incorporate the user feedback during the model training itself, and not during the interaction with the interface. And so to highlight this idea, we propose the following research questions. The first research question is about how the agent, that's what we call our learning model, how the agent would see the world around it, how it can observe, or what is its view of the world and of the user. In terms of, as I said, sensors, what kind of sensors it needs, what kind of observation it should look at, but also it could also be thought as what kind of feedback it can get of the user. Is it also, there was a question in the keynote this morning about if we can narrow down the realm of possibilities that we could adapt to. So this is exactly what this research question is about. If we can, let's say, include only the properties of the users, like their age, their gender, their way of handling things, like if they are right-handed, left-handed, and so on. The other research question is the multimodal interaction one, and this aspect is related to the underlying model. Which model and what learning model can we use to actually do this kind of multimodal fusion between this different kind of sensors and interaction. The third one is the neuro-symbolic adaptation, or what we also call personalization, and using continual learning to have a kind of a lifelong learning scheme where the model is continuously adapting and not just have like a rigid model that you could use and take a snapshot of, like you could go back to our previous snapshots or things like that. We want to actually keep tuning the model and keep training it all of the time. And to give more concrete ideas about the solutions that we had from our previous work as well, I'm going to talk about an application in the automotive domain, and then I'll highlight also our current or future work relating to robotics domain. So in this special case, or this special use case, we have a use case of users trying to reference objects while they are driving a car. So this is basically just while I'm sitting in a car driving like that, and I'm trying to say what is this building outside, asking the car concierge about something about it, or telling the car to park me there. And we are concerned with this exact problem of how to identify where you are referencing. Through speech, through pointing, through gaze, through head mimics, and so on. So to map it to our methodology or our research questions or the guidelines that we are proposing, first things that we look at is what is the agent world view. So what does it observe about the world? What kind of information should we actually give this agent? So for example, we have a mental model of how the users behave based on our collected data. Like they do a couple of gazes. You can see up in the screen things. So they do a couple of gazes and then they do it before pointing, after pointing, during pointing. But this is about the temporal dependency of this kind of gestures. The second step, how can we actually combine those together? So there's multiple ways of fusing modalities. And you could use early fusion, late fusion, or use a kind of hybrid fusion where you actually insert this knowledge. And that's what we also try to deliver with the same idea. So I'm going to talk a bit about it more when I get to some of these results. And the last thing, how can we do continual learning? And what we propose for that is for use incremental learning approaches that is quite known in the classification domain. But instead of using it for actually assuming that data doesn't come continuously, we assume that we have all of the data, but we want to apply it for personalization. Again, I'm going to delve a little bit in the details in the next slide. So what we did here is that first, in this image, we tested out and tried out different ways of using the model, like this exact example that I'm talking about with vectors for referencing. We take the raw vectors from, right? We take raw vectors, now it's completely gone. So we take raw vectors from the data, and we try to train a classifier or a regressor directly on this raw data, and this is what is called an early fusion. But we also try different ways of training a separate model for each of them and combining them at a later stage, which is called late fusion, and try a hybrid learning approach where right here we collect the participants, collect their behavior, and calculate some kind of pseudo pointing and gaze accuracy metric. And this is the insertion of our rule-based approach. And based on that, we run a clustering model right here. So this image is zoomed in from that one. So we run our own clustering method to identify or classify the users into different clusters. And based on that, we could say, okay, whenever we get a new user, we are going to automatically say this user is belong to this group. And based on that, we're going to take these specific models that we trained for that group specifically. And when we tried something like that for each participant, we could also see that here in these two curves, we could see that personalized participant, here this is RMSE, so the lower value is better. When you increase the weight of, or the influence of a certain participant on your model, you get a better accuracy for that participant specifically, while not actually degrading that much for all of the other participants. But at some point, of course, you overfit and get a very bad results for all of them. But this is one way of doing the fine-tuning. We did it with incremental learning approach and support vector regression. But we are also trying to do that for a model agnostic way, where it can work for multiple deep learning and machine learning models. So to conclude for that part, we found out that there is no global solution that fits all participants or all users or all data in any kind. It actually doesn't have to be with a user interaction. It could be that you have data from different domains and you want to adapt to a certain domain, because you get this very high variance in this user behavior. And most of the current data-driven approach, they focus on this implicit feedback kind of way. So they get this sensor data or this sub-symbolic data from the features or from sensors that they have, but they don't get this explicit feedback, and that's what we are trying to do. And that we need an incremental learning or a continual learning methodology that could be adapting to the changing behavior over time. So it's not something that is fixed, but it's always changing. And to also give you a brief of what we are currently working on, how we are continuously adapting to this. So in our current work, we continue with the same idea, the same application, but to propose it in a better way, we also showed that it can adapt to the same user. So I think the font is a bit small here, but it can adapt to the same user in different conditions. So if the user, for example, is wearing sunglasses and then the eye tracker is no longer can track his gaze. So with using a generic model, like the ones usually deployed in the current system, it will not be able to handle this rapid change in the feature set. Also, if you get a different user, and this is the personalization part I'm talking about, the whole metrics or whole feature aspects will be completely different from the previous user driving the car. And that's when this personalization aspect takes place. And to test that out, we did it also for different personalizations. This is a current work. There's a lot of other results, but I'm going to not delve into that now. It's still in submission. So with that, we could also show that with our incremental learning model, which we call IC regress, here this is accuracy instead of MSE, so it's more reflective and the higher is better. We get much better accuracy compared to using a generic model for all participants, or training from scratch for this participant specifically. It will work quite well to it, but it will be performing very bad for others. Or doing a transfer of learning or a simple fine-tuning, where you take the model and just fine-tune it in the new participant without using our own way of including the previous data as well in this incremental learning approach. We also try to do that in other domains as well. If you have been here for the talk yesterday, I already gave a brief about this other work in the reinforcement learning part, but we also look at it from the adaptation side. So how can we include the surgeon in the loop when trying to train an agent that could actually perform a part of surgery? It sounds dangerous, but we're using only for simulation, and it is only a small part for the surgery itself when it does the incision without breaking the eye. We also are checking that or working on this with anthropomorphic grasping, where you have a robot with 5 fingers that has the same joint exactly as a human. How can we make it learn like a human? So when you try to grasp an object, every human do it differently, and hence you need again this kind of adaptation for specific behavior from humans, for a specific object, or for a specific task. And that's why it's a task-aware anthropomorphic grasping. So thanks a lot for listening. So these are my references, and I'm open for question. Just to mention, this is a extended abstract paper, so the full paper was an AI and HCI workshop at the ICML, and you could also see it next month at ICME Blue Sky paper. So. This one. There's another mic? No, I think it's
We have questions online. I can see. Alina, can you tell me if there is someone?
No, we don't have anything.
Well then, thank you. Thank you. All right, so we'll move to our second presentation. Laura. All right, the second paper is titled Can Large Language Models Demystify Live Reports by Laura. Welcome. Sure.
Okay, so hello everyone and welcome to this presentation for our paper. So can large language models demystify bug reports? So every day many bugs are getting reported for many software projects. So it can be very annoying for users once they discover a bug, they report it and they have to wait for hours or days until the bug gets fixed and they can continue their work. But additionally, they become quickly overwhelming for developers of projects which just keep seeing new bug reports getting reported the whole time. So bug reports, they can be just as GitHub issues or on different website, depending on which software project we are considering. So currently we have this huge amount of bug reports, but we are lacking the tools to automatically address the bug reports. So to address the bug, so first step is of course for the human that discovered the bug to report it. And the second and most important step is then, how can we now reproduce the bug and first verify that there actually is a bug and really clearly see what is the problem. So therefore, usually we write test cases, and if the test case fail, we will what we will call here have a so-called bug triggering test case. So afterwards, once we have a test case and understand what the actual problem is, then we can start localizing the bug and fixing it. So either the developer can just manually fix it, or we can use automated program repairs to directly fix the bug. So nowadays, when the bug gets reported, we most of the time cannot directly apply their automated program repair tool since we only have the bug report. So also in software, of course, the software is heavily tested before it gets deployed, but usually the test suite are still incomplete. They just cover like simple unit tests of the software. And it's only once users start to have more complex user executions that we really see more complex bugs. So for those more complex bugs, we usually still need the informal human input to clearly define what is the expected outcome that we expect from the program. So what we clearly need here is an automatic way to generate those kind of bug triggering test cases as soon as a bug is getting reported. So if we have a look currently at automatic test case generation, we have some very useful tools such as EvoSuite and Redup, which are currently used a lot to generate Java test cases. But the problem here is that they all require some form of specification. So if you have the source code and you want to generate test cases for a specific function, they are very useful. But if you have no clue of what the problem is except the informally written bug report, you cannot apply those tools to generate more test cases that will actually help you address the bug. So if we would be able to generate test cases which actually tackle the reported bug, we could also afterwards directly use automated program repair tools. So here on the overview, we have our standard automated program repair pipeline. So here I took the example of TBAR, which is a template-based automated program repair tool, which just tries to apply several fixed patterns until one of them fixes the bug. But in order to do so, a first step is to localize the fault in the source code. So therefore, we already usually need the failing test case in order to localize the fault. Therefore, you can use, for example, spectrum-based fault localization. And based on that, you can start generating patches. But of course, at the end, you also need some kind of verification. Is this patch now correct? Therefore, you usually then reuse the test cases. And once you pass the previously failing test case, you have potentially fixed the bug. So by generating by automatically generating these bug triggering test cases, we can not only reproduce the bug, but afterwards attempt to automatically fix the bug. And of course, also in general, improve the software quality and making it more robust for future changes. So as we saw previously, what we have as input is all the users reporting the bug. So we thought, okay, so let's try to use the bug reports because this is the information we are getting from the user. So the idea is we have the bug report and what we want is a test case that actually reproduces the bug. So then the question is, well, how can we now generate those test cases and try to address the problem? So we have seen that large language models have shown many successes. So here are just a few examples. I know there are many more, but traditionally, most language models were really focused on natural language, but very soon they have also been fine-tuned for code-oriented tasks. And now lately, with the arrival of ChatGPT, we have seen a model that is good for natural language tasks as well as also for code tasks. So for example, for code translation from one programming language to another, code summarization or documentation generation. So we have seen many successes in software engineering in that area. Therefore, we came to our main research question, which is, can ChatGPT demystify bug reports? So what do we actually mean by this term of demystifying? So the general question was, is it feasible to use those large language models to actually translate those informal bug reports into executable bug triggering test cases? So how did we do that? So for our experiments, we worked with the Defects4J project. So Defects4J is a database of existing real faults of many Java projects. So these collections come with the projects. We have the bug report, so we have the title, the description of the bug, the exact buggy version, because of course we need the buggy and the fixed version of the project to see if our test cases are actually helping to address the bug. So here for the model in this experiment, we will be using ChatGPT, but it could be any large language model. And so the idea is just to generate the test case and then we do our evaluation. So for the Defects4J, it actually consists of many different projects. So here we focus on these 6 main projects, which are currently mostly used in the automated program repair community. So here we have a certain amount of faults that got reported for the project. But here, the number of bug reports is a little bit less because for some bugs, the bug reports are not available anymore, or there were also several duplicates. And of course, I didn't want it to take duplicates to not get wrong results. So for ChatGPT, at the time we did the experiments, we used their 3.5 version. And so as evaluation, of course, the first criteria is that the test case has to be executable, because we all know that ChatGPT can be very helpful, but sometimes, yeah, it's, let's just really say, useless. So the first step was to see if the test case actually executable. Then we defined validity as the fact that the test case has actually to fail on the buggy project, because otherwise, for sure, we are not able to actually demonstrate that there is a bug in the project. So then in general, just the research question was, can we translate those informally written bug reports into executable test cases? So since we worked with ChatGPT, we simply used the API, and I used a very basic prompt where I just told ChatGPT, write a Java test case for the following bug report, and I just appended the bug report. So for the bug report, I didn't do any pre-processing or anything because I wanted to see if it's actually applicable in real world, because automated program repair tools are all great in theory, but the problem is that we cannot really apply them to real faults. Therefore, I just took the bug report as it is. And here we have a first example of a generated test case by ChatGPT. So as we can see in this example, it clearly catches some semantics that the user reported. So it clearly reused the parser that the user reported, their inputs were also correct, and it was an executable test case. So this was the example of the Kljun project, so it was a specific bug. And if we compare to the original test case that developers wrote, it's not the same, but we can see that clearly it catches the semantics of the problem reported by the user. So more in general, we repeated this for all the projects of our study. So each time it's just the instruction to generate the test case and the bug report. So as we can see, their general executability vary greatly depending on the project, which can also be due that different projects collected the bug reports differently. So for some, it was just a GitHub issue. For some other project, it was a much more detailed bug report. So this can, of course, then influence the quality of the test case generation. So in general, what we found is that 50% of all the bug reports, for 50% of the bug reports, ChatGPT was actually able to translate them into an executable test case. Overall, we had 30% of the bug reports that got directly translated into valid test cases. So the first kind of challenge is to really get executable test cases. But once you have executable test cases, then actually 59% of those were really reproducing the bug. So this can already significantly help to automatically address half of the bugs. If you can address half of the bugs automatically, this would already be a huge gain. So we also had a look at a more newly reported bug. So as we all know, ChatGPT and many other language models have been trained on a huge amount of publicly available data. So here was, for example, a bug report from April 23. So clearly, for sure, not in the training data of ChatGPT version 3.5. And as we also can see in this example, ChatGPT was able to take the important parts from the bug report and translate them into an executable test case that reproduces the behavior from the user. So, of course, here, this was a first work on really showing the feasibility of the idea. So here we use the Defects4J dataset, which only, for example, contained Java source code. So in future work, it would be interesting to also give it a try, for example, for Python or other commonly used programming languages, since also there we have many bugs that are getting reported on a daily basis. Also, at the time of the work, we were only able to use ChatGPT version 3.5. Now it's even available for fine-tuning and more powerful models came out. So of course, it can be interesting in future iteration of the work to see how we can improve the performance. But here the main goal was really to show the feasibility of the idea. And in future iteration of this work, we are working on actually trying to really improve the performance to get a higher amount of executable and really relevant test cases. An additional important part is the executability of the test case. I mentioned that half of the bug reports got translated into executable test cases. But here I took the output from ChatGPT really from scratch without doing any manual changes. So one very common issue was that sometimes ChatGPT forgot to generate the imports. Well, if you want to do an assert and you don't import asserts, of course, it's not going to be compilable. So if we would just either change the prompt and directly ask them to explicitly generate the imports or do some small changes afterwards, we could have a much higher number of executable test cases. Another issue is also that some functionings were duplicates because, of course, the test suite already contained many test cases. And if you clearly state which function caused the problem, it's highly probable that ChatGPT uses this as a new test case name. So this was another issue that I encountered while having a look on why it failed for some cases. And sometimes just using a deprecated function that is not used in this specific Java version. So here with the small changes in future work, we should be able to significantly improve the amount of executable test cases. And of course, I mentioned the motivation for automated program repair. That also in future iteration, we did some work on really having a look at how we can improve the actual photocardization and patch validation process to really have it usable in real software projects. So in general, our study showed in the first step that ChatGPT was indeed able to generate executable and valid test cases. We also investigated that it's actually able to generate them also for newly reported bugs. And in general, the generated test cases are helpful in general for software engineering in a first step to reproduce the bug and afterwards, of course, to improve automated program repair. So as a conclusion, we can say that indeed ChatGPT can demystify bug reports. So all we need is a human to actually report the bug, and afterwards we can automate the process to actually address the bug. So thank you very much for your attention, and do you have any questions?
Thank you for the presentation. I have a question about the results. You mentioned 30% of the back reports came to a 25 test. Is this 30% out of the 50 that is also executable, or total amount of?
So the 30% was from the total amount, but from the 50% that were executable, 59% of those were valid. So the really main challenge is to get them executable, and then over half of the executable ones were then really valid test case that reproduce the buggy behavior.
See, and what next did you use to validate that the reports, the back reports are actually valid?
So in
the bind report, check one by one.
So for the bug reports, since I worked with the Defects4J project there, the bug reports that were really labeled as bugs in this project there, in the past developers really checked if it was really bugs, and those bugs got already fixed. So there we know for sure that it was really a bug in the software. I didn't consider any bug reports that were just labeled as issues, because on GitHub you see many issues where people say it's an issue, but it's not actually a bug. So here I really focused on real bug reports that got clearly labeled as bug by the project developers.
Did you have a chance to compare ChatGPT generated test cases versus test cases written by experienced developers to see the difference? Because if there are some differences by ChatGPT, or you can maybe do the other way, which is developers themselves in writing the test cases.
What exactly do you mean by comparing them?
So if you compare test cases and say this as to an experience developer the terms, then you compare.
So for the comparison, we did on one hand some manual investigations to clearly see that they are different from their original test case while still capturing the semantics. In some future iteration, we did some more detailed analysis on the complexity of the test case and the further relevant, but I don't want to spoil too much after the further iteration of this paper.
Thank you, Laura. So the last presenter of this section is Nuwan from Koper, Slovenia, presenting a paper titled Missing Interface. It was no interface, no problem, right? Yeah. Yes. Okay. Welcome, Nuwan. You have 15 minutes.
Okay, thank you. Okay, good evening, everyone. Everyone can hear me. Yeah? Okay, so good evening, and I am Nuwan Attygalle. I am finally a PhD student at University of Primorska in Slovenia. So I am working at with the HITLAML' group in University of Primorska. So today we are going to discuss about gesture recognition on everyday objects with radar sensing. So I'm very interested in gestures. So gestures can be divided mainly into two categories, media gestures and stroke-based gestures. So what we are doing is here in this work, we are studying the feasibility of performing media gestures on everyday objects. The application scenario is like this. So let's imagine a situation that you're driving your car and you're getting a call. So in order to answer the call, you don't have to take your hand out and go put some buttons. You don't have to push the button, but you can just answer the call by just putting swipe up gesture on the steering wheel. And the most important thing is that you don't have to put any sensor on the steering wheel, but still you can perform gestures and you can interact with the systems. So this is the whole idea of interacting with any object using objects in the real world as interface to communicate with digital devices. Also, another scenario is like, let's imagine a situation that you are cooking and you are cutting some vegetables, and suddenly you hear your favorite song played on the radio. So in order to increase the volume, you don't have to go to the radio, but still you can increase the volume by performing swipe up gesture on the handle of the knife. On the handle of the knife. So, you can perform the swipe up gesture and it will increase the volume. So again, I emphasize that you don't have to put any sensors on the knife. You can do gestures and you can interact with the digital systems. Okay, why we are so fascinating about gestures? Gestures are very natural for humans to communicate. If I do this, you all understand. Okay, like this is the gesture for standing up, yeah. So and this is the gesture for. Okay, so you're doing great. I think I am. Okay. Anyway, so these gestures are very intuitive for humans in communication. And even babies use gestures, So when babies does this, they are very hungry. And when babies does this, that means they are full. And they do this even before they utter their very first words. So because of this, gestures are very intuitive and natural in human communication. Also, so with human-to-human communication, gestures are very natural and intuitive. When we talk also, when I'm talking, I move my hands a lot, so But in SCI, in human-computer interaction, it's going on a transformative shift towards mouse and keyboards, these traditional interactive methods, to more natural and intuitive interaction methods, such as gestures. So because of this, that's why we are very, very interested in gestures. But most of the day-to-day items are not built with interaction capability. So for an example, if I want to now, okay, so see, when I close to the mic, so I feel like my voice is not adjusting so much. So then if I can perform swipe up, swipe down gestures on this microphone, then it would be better. So, but this mic is not built in with this capability. But what we want to do is we want to make every day any object interactable. So we are using millimeter wave radar to do so. These existing gesture recognition methods, you can use camera-based sensing and acoustic sensors and capacitive sensors. But the problem with camera-based sensors, you have to, this camera it should not be occluded by the material. So this visible light cannot penetrate through most of the material. So because of this, it cannot see and it cannot identify gestures. Because of this, camera-based sensing fails when it comes to perform gestures identify gestures with materials or everyday objects. Acoustic and capacitive sensing can be achieved. So they can penetrate through materials, but they are lack of spatial and temporal resolution. Because of this, millimeter wave radar have an advantage over existing recognition methods. So why particularly millimeter wave radar is, millimeter wave radars are not affected by lighting conditions. So those are work during the day or dark night. So it's not affected by the lighting condition. And also it's very robust for different weather conditions. That's why these radar sensors are embedded into automotive cars. And it's very compact in sizes. So in compared to this is the solid sensor that we are using in our work. And it's really small. And it has higher spatial and temporal resolution because you can sample in very high frequency. So because of that, it has higher temporal resolution. And also you can increase the spatial resolution by increasing the number of receiving antennas. And also you can have, you have these advanced techniques like MIMO, so multi-output, multi-input ways, so you can multiply the number of antennas. And also, most importantly, with millimeter wave, you can sense through non-conductive materials. So this is why we are using millimeter wave radar sensors. Okay, so to study the feasibility of executing gestures on objects, we define these gestures, set of gestures. So we have our picture frame, and we are performing one set of gestures on this front interface of the picture frame, and the rest of the gestures are back. So you can see this blue color finger is indicated where you use to perform the gestures. So in one case you perform gesture in front of the picture frame, and in the other case you perform gestures behind the picture frame. So the picture frame occluded your finger. So why is it difficult to sense gestures through materials? So when this electromagnetic radiation penetrates through materials, going through material, it has this signal distort because of the polarization or scattering. It can be scattered, it can absorbed by the material, or it could refract or reflect from the properties of the material. Because of this signal distorts a lot. Because of that, it's very challenging to perform and identify gestures that performs on the material or through the materials. Okay, so this is the whole grail of this. So this is the radar equation. So I would like to highlight two terms in this radar equation. This is radar cross section and signal to noise ratio. So radar cross section is really relates to the so we are performing gestures with our hands. So this is the radar cross section depends on the hand, the area of the hand, or the characteristics of the hand, and also the signal to noise ratio. So let me explain this, the importance of this with okay, so where's the mouse? Okay, so you see this plot, this with this plot, it shows you the some peaks. It shows you some high peaks, and it's very lower peaks. When we extract this interested region, what we are doing is we put a threshold line. So let's say we put a threshold line between 0 and 1, and we consider all the signals, all the peaks that are above the line that we are defining are as signal, and we ignore all the peaks below that line as noise. So this is how we do this. Okay, so just keep in mind, I will come back to that later. Okay, so when we are calibrating the sensor, we have to provide this threshold. So what is the threshold level that we are considering as signal, and what we are considering as noise? So most of the time, up until now, most of the researchers have considered this as a fixed line. So they fix the line between the noise and the signal, and they put that as fixed, and they do their gestures. Okay, so we define our research questions and as so first research question is, can we use radar sensing to identify gestures on objects, and how this decimal range, so decimal range is how this threshold would affect the gesture recognition performance, and this threshold level is user dependent. Is it depends by the user? So as I mentioned earlier, so this signal to noise ratio is depend on the properties of your hand, and the properties of the hand varies user by user. So they have this moisture content, and the texture of the hand is different from user to user. So because of that, we hypothesize that dB range can be user dependent. What is the potential gain of calibrating the dB range correctly, and how to do this? How to identify rather than fixate in this decimal level? how to characterize this decimal level to maximize the recognition accuracy. Okay, so to address these questions, so we designed our gesture set. It's like this. And we designed our experiment. So you wear your radar sensor on the wrist, and you hold the picture frame. So we chose picture frame because it's very available, and it's made out of wood and glass and some paper in the picture. So you hold your picture frame with your finger and you perform gestures on it. So this is our experiment setup. And for data collection, we performed 11 gestures with 10 users, 6 males and 4 females in age range between 23 and 50. And each user would do 20 repetitions and within 3 to 5 sessions. With experiment, we chose the data representation technique as range Doppler images. So range Doppler images are very known in signal processing community. What range Doppler images does is, in one axis, it shows you the range of the target that is moving, and another axis, it shows the velocity, in which velocity the target is moving. So it's a graph that shows you the range and the velocity of the moving target. And we chose range Doppler images based on the previous research, and also this another signal representation method. We use spectrograms. So these are the two methods that we use in order to input the signal into the machine learning networks. Okay. So then we designed 3 model deep learning architectures. Hybrid. One network is based on convolutional layers, and we extract the features from convolutional layers and then fetch the extracted temporal features into LSTM layer, and then we do finally the classification. And the other network architecture is based on convolutional 3D layers, and the final network architecture is based on convolutional, just 1D convolutional layers. Okay, so to find out more detail about the model architecture, I invite all of you to read our paper. So training and evaluation, we use this standard parameters, these hyperparameters for model training, and you can find more information about this in our paper. And in data partition, we use 50% of the data as the training set, and 20% as the validation, and 30% as the test set. So we made sure that our models are very generalized. Okay, so to evaluate the model architectures, to know whether our model architectures are good enough, so we evaluated our model architectures with existing datasets on interacting with Solling paper. So we achieved around 99% accuracy with our models. So to select optimum dB range setting, so to identify, okay, so it's very far back. So identify what is the optimal threshold dB level, the threshold level. Yeah, so we did this experiment. So we trained all these 3 models with different dB ranges, 32 to 0, 16 to 0, and -8, -4, -2 to 0. So with varying the decimal range. And we repeated this 3 times with different train partitions and validation and test partitions. So especially the test partitions were not, each time the test partitions were different from each other. So we repeat the experiment 3 times and we put the average. So we did this because we did this to make sure that our models are very generalized. Okay, so you can see this -2, -4, -8, and from -16 to onwards, this accuracy, there's a significant difference of this threshold level. So this shows you that if you have a lower threshold, that it's better to have lower threshold level rather than having a high threshold level to identify, to distinguish the actual signal from the noise. Because these deep learning networks are very robust against noise. So when it's trained, it actually it actually varies the threshold level in order to maximize the accuracy. So here we conclude that it's better to have a lower threshold level between the signal and the noise. So the deep learning network can really adjust the determine the threshold level. And we wanted to, so the next hypothesis that we wanted to test is whether the dB range setting is user dependent. So this threshold level depends on the properties of the hand. And to do this, we group the gesture set by users, and we again train the networks, and also we experimented against the different different dB ranges, and we repeated these 3 times and took the average accuracy. So you can see the dB range is among all the users. You have a higher accuracy from -8 to 0. So we observe the last trend in here as well. So the dB range is not really depend on the properties of the user. Okay, so once we chose -16 as the optimal threshold level. So you can put you can choose -16 to 0, or you can use you can use higher level as the threshold, and we trained our model. So for 11 gestures, we acquired 79% accuracy, and for 5 gestures, so these 5 gestures were non-directional gestures, and we acquired 93% of accuracy when performing gestures on top of the objects. And these are the confusion matrices. And so the takeaway message is that it's good to underestimate the signal to noise ratio rather than overestimating. And also it's possible to perform gestures on top of the objects. And if you do directional gestures, like you have swipe up gestures and also you have swipe down gestures rather than swiping up and down gestures. So these swipe up gestures and swipe down gestures, we call these as directional gestures, and swipe up and down gesture. This is a non-directional, bidirectional gesture. So our models are very bad at identifying, distinguishing between directional gestures. It's because we are using range Doppler images. With range Doppler images, you have ranges and the velocity. Only you have the velocity and the ranges. So with directional gestures, it's the same. So because of that, so these are the limitations, but in our future work, we are addressing this issue with incorporating angle Doppler images and range Doppler images all together. And we are considering other reprocessing techniques, other features as well. Okay, thank you very much for your attention. And if you have any questions, I'm more than happy to answer. Okay. Sorry, I did not get the in one case to find out. So in the experiment that we wanted to find out that whether this dB range is user dependent. So we wanted to identify, address this question. In that experiment, the experiment was designed in user dependent way. So we put user as the parameter that we vary, and the accuracy as the parameter that we are not. It is the independent variable. But the other question. Okay, sorry. Okay, so in AR environments,